Okay, which secrets are we talking about? Oh dear, let me just get, there we go. First secret, how pure is the product? We're going to be talking about minerals, fillers, and extenders predominantly, because that's my area of expertise. How pure is it? Has the product, and also has the product been diluted to make it cheaper? That's useful to know. Secondly, is this product calcined? Usually they tell you if it's calcined or not, but there's a secret in the data sheet that can confirm that, and I'll show you where to find that. What about upsizing opportunities? Interesting terminology, and I'll tell you about that as I get to that topic, and it's to do with saving money. Then, how white is it? And how yellow is it? Always useful to know how yellow something is for the paint industry. Nobody likes a yellow product. And then finally, will it give good scrub resistance to your paint? So let's dig into this. How pure is this mineral? You've been presented with a mineral and you've got the data sheet. Where do you go to look at purity? So the obvious place is the chemical composition. And the trick I want to tell you about is to compare the chemical composition given in the data sheet to the theoretical value of the absolutely pure mineral. And how do you get to that? So let's use kaolin as an example. Kaolin is aluminum silicate, and this is one of the ways you can write the chemical formula of kaolin. Alumina, 2 silicas, and 4 waters of crystallization. And, you know, if you're a chemist and you know about molecular masses, you can work this out from first principles using the molecular masses and the molecular mass of the whole molecule. Or you can just Google, amazing Google, what is the theoretical composition of pure kaolin, and you should get to this. So it's roughly, for pure kaolin, no impurities, 46% silica and 39% alumina. Now, these do not occur separately as silica and alumina. They are locked up in the crystal structure of the kaolin, which looks like this. So you've got the alumina atoms, silicon and oxygen atoms, and the OH groups. So they just report it as alumina and silica on the data sheet, even though it's in a crystal structure. So here's an example of one of the kaolins that we import. And if we go to the chemical analysis here, silica and alumina are usually the first two that you see for kaolin. This kaolin has got 47% silica and 37% alumina, as you can see. Now let's just quickly go back. Theoretical composition of pure kaolin, 46 silica and 39 alumina. 47 and 37. So they're within a percentage point or two of the theoretical composition of pure kaolin. So then you know, it's pretty pure, this kaolin. You can almost never get pure kaolin unless you are synthesizing it in the lab or in a plant, and nobody really does that. So, and you can reconfirm that it's quite a pure kaolin by looking at the rest of the impurities here. They're usually 1% or less is pretty good. This one has got quite a bit of titanium. Another hint that this is probably a pure kaolin is that it's hydrous. And hydrous usually means that it's water washed. There's two ways to purify kaolin when you have a kaolin deposit. You can either water wash it, which is a very effective way of removing the impurities. The main impurity that occurs with kaolin is silica. That's what we had when we had our kaolin deposit, and mica was the second largest impurity. And the water washing process separates on particle size using hydrocyclones, and it takes out the biggest particles. Luckily for us, the biggest particles were silica. And then the next biggest ones were mica. So that's how we got nearly pure kaolin. This is an imported water wash kaolin from India. So you can see, not surprisingly, it's quite pure. So once our kaolin plant closed, it was the only water washing plant in South Africa. There's no more water washing of kaolin in South Africa, the only process used for beneficiating kaolin is milling. So this is an example of a milled kaolin, also one of our products produced locally. They just dig it and mill it. There is some classification, usually air classification, to remove the very biggest particles, which are usually silica. And then the rest is milled all together. And look how the alumina and silica values are different. 24% alumina and 67% silica. So it's way off the theoretical composition of pure kaolin. And what it tells you, when you see a silica content in the 60% for silica, for kaolin, you know that it's contaminated with silica impurity. And this is free silica, also known as crystalline silica or quartz. And it's usually not a problem. This type of kaolin is an impure, cheap kaolin. It's just been milled. The fact that it's got some silica in it is not a problem for the industries that use it, usually adhesives, rubber, and the ceramics industry uses silica anyway. So they're quite happy with a bit of silica. So quite a good way to find out if that kaolin is a pure kaolin or not, or close to pure. Another example is talc. Talc is magnesium silicate, and its chemical formula can be written this way. It's magnesium oxide and silica. Also not separated, they are in the crystal structure of the talc. And the theoretical composition for pure talc, again, you can work it out or Google it, 63% silica and 31% magnesium oxide. So here's an example of the chemical analysis of off the data sheet of microfilm 20. It's talc that we import from India. And you can see the silica and magnesium oxide are quite close to the theoretical content. 61 and 32. I'll just quickly go back. 63 and close to 32. So that tells you this is quite a pure talc. And it's confirmed by the lower presence of other impurities. They're all less than 1%. So yeah, a pure talc. However, there are some talcs on the market that are contaminated with calcium carbonate. I used to think that it was a way to cheapen the talc, but I've met a talc supplier from India at the recent coatings show, and he told me that they have calcium carbonate that occurs in the mineral deposit, in their talc deposit. So sometimes there's calcium carbonate contamination that way. And when you measure calcium carbonate for chemical analysis, it reports as calcium oxide. So here, oh, red flag, 15% calcium oxide. And then these are not close to the theoretical values. So that shows you that this talc has got calcium carbonate in it. Either as an impurity in the original deposit, or perhaps somebody has added calcium carbonate and mixed it in with the talc to make it cheaper. If you get offered a very cheap talc, have a look at the data sheet, look for calcium oxide, and if it's 15%, then you know there's calcium carbonate in there. If I just scroll back to this talc, you can see it has a very low calcium oxide, less than 1%. So it hasn't got calcium carbonate added or as an impurity. Right, and the next secret is this product calcined or not? So often it would say that it's a calcined kaolin or calcined alumina or whatever. So the way to find out or to check whether you definitely is calcined is to check the LOI. You might have seen that on data sheets and wondered, what is LOI? Right, here's the definition. When you measure the LOI in the laboratory as part of your developing the data sheet, you take a sample and you vigorously heat it so that all the volatile substances in the sample escape until the mass stops changing. So you measure the mass before and after, and the difference is what's called LOI, loss on ignition. Right, so what volatile substances are there? So for example, you go to the kaolin, here's what's volatile. I mean, alumina and silica obviously aren't volatile. You heat them up, they're not going to evaporate. But water, you heat it and it will evaporate. So the volatile component of the kaolin structure is the waters of crystallization. So they are what will be volatilized when you heat it up. So there will be a loss of on ignition. The mass of the water will be the difference. And if we go back to our example of the kaolin I showed you before, you can see LOI is at the bottom here, 13.5%. So that means 13.5% of the mass is the waters of crystallization, and measuring and weighing it before and after vigorously heating it, 13% is the difference in mass. So what happens when you've got calcined kaolin data sheet in front of you? This is the data sheet for the calcined version of HW powder that I had before. And you can see the LOI now is 0.5%. So that's what you expect. It must be nearly zero because the kaolin's already been calcined. So it's already been taken to 1200 degrees. It's lost its waters of crystallization, and that changes the crystal structure, but which is what makes calcined kaolin such a good opacifier. And then there's no more waters of crystallization to lose. So the LOI would be a very low number, nearly zero for calcined products. Right, next secret, upsizing. Oh, what is that? The clue is in the word size. Check the particle size. So upsizing is a term that I coined just to have a nice catchy name for using a coarser grade to replace a finer grade, because as you go finer, a product gets more expensive. So if you could replace a fine grade with a coarser grade, you can save on your input costs. So for the example here, this doesn't always work. So you have to look at particle size and see if it's worth trying. But we found, for example, Ascom 10 is a calcium carbonate that we import from Egypt. It's a 10 micron calcium carbonate with a D50 of 10 microns. And the deposit in Egypt is a very soft limestone, so it mills very easily. And they struggle to stop the milling at 10 microns. So our Ascom 10 has got a D50 of actually 6.5 microns. And if you compare that, for example, to Ascom 5, the 5 micron equivalent, which has got 5 micron D50, average particle size, and also other competitors of 5, the Ascom 10 with a D50 of 6.5 is quite close. So maybe you can use Ascom 10 to replace a 5. So it's just a trick, a suggestion. Try it and see. It might not always work. Sometimes you don't get the results, or the product is worse off than before, then don't do it. But if you can do it, you can save on cost. Right, talking about particle size, the problem with data sheets is not everyone measures everything the same way. And sometimes you get the particle size reported as microns and sometimes as mesh sizes, especially these minerals from India and China are often given, the mesh size is given, not a micron size. So just as a definition, microns are 1/1000th of a millimeter. Your hair, for example, is a 50 micron diameter. If it was 40 microns, it would be invisible. The symbol for micron is either a U or the Greek symbol mu, I think it's called, mu. Okay. Or they use UM or mu-M. And the mesh, definition of mesh is the number of yarns per inch of filter cloth. This was the old way of measuring particle size, where people wanted to know what size of particle would be held back by a certain mesh filter cloth. So the number of yarns per inch. Obviously, if there's lots of yarns in an inch, it's only very small particles will go through. And if there's only a few yarns, then bigger particles will go through. So that shows or indicates that there's an inverse relationship between mesh and actual particle size. If it's a high mesh number, it's a small particle size, and vice versa. The symbol for mesh is the hash sign. The way to resolve this problem is to use a conversions chart, and we've tried to make things easier by having a conversion chart on our website. It's a very easy to remember website, kaolin.co.za. And this is what it looks like, conversion chart. The one tricky thing is that there's quite a few different mesh standards. There's the British mesh BSS and the American mesh standard, and there's two more. So you need to know which one you're using, and hopefully they will mention on the data sheet it's so many mesh using the BSS mesh formulas or the ASTM or whichever. So once you have a mesh size on your data sheet, you go across on the conversion table. For example, 100 mesh is 150 microns, 4 mesh is 4,000 microns, the inverse relationship. And the mesh sizes go up to about 2,500 mesh, which is equivalent to 5 microns. So use the conversion chart. Again, you can just Google and find one. Right, the next question is whiteness. Now, this is something at the top of mind for most producers of paint. Again, the problem with whiteness is that it's called different things and it's measured different ways. Sometimes it's called whiteness, then it's called brightness, then it's called reflectance. So how to compare one apples with apples, one product with another, you have to know what they're actually measuring. And they usually tell you. Most mineral suppliers have a spectrophotometer, and the spectrophotometer machine does spell out all these results. They call different things, and they're at different wavelengths. So all the ones that are highlighted here are used for whiteness, in my experience. Maybe there's more, but these are the ones I've found. So sometimes it's called Y, sometimes it's called L, which is sometimes called lightness. Sometimes it's called, they use the RY wavelength. And the R457 is the most common one for kaolin, and that's the one that's 57 and reflectance are all the same. You don't have to try and remember all of this. I've got a whole article that you can look at on our website, and it's got all this information. It's a bit difficult to remember all of these things when you don't deal with it every day. So here's just to show you the whiteness line in this kaolin example that we've been using. Okay, we drew this up, so that's why I put iso brightness stroke reflectance, and it's measured using the El Refro spectrophotometer at the R457 wavelength. 79%, that's not very white. Whiteness, you'd like to get as close to 100% as possible. Titanium dioxide, as everyone knows, is the whitest mineral, and it's very close to 100% whiteness on most of these parameters, even on all the wavelengths, actually. 99.5 usually. And this is an off-white kaolin, so it's only 79% on whiteness. Now, here's another example. This is one of the calcium carbonates from Egypt, from ASCOM 2. And the whiteness in the top line, they call it whiteness RY. So they are using the RY wavelength from the spectrophotometer. So if you want to compare, just say this calcium carbonate with another one, and they are using another one, maybe they're using reflectance, R457. So they probably have the RY value, and you can ask them, because their spectrophotometer probably does, they can get it from their spectrophotometer, they can get their RY. And then you can compare apples with apples. Or you can go to ASCOM and say, can you please give me the R457 value for whiteness? And then again, just say one is whiter than. Then you can say from the data sheets whether one's whiter than the other. Of course, most people just put it in their paint and check the drawdown. And you can do that too. Okay, how yellow is the product? That's another parameter that you can find on the data sheet, or at least if it's not on the data sheet, you can ask the supplier. And the yellowness is reflected by the B value. If you remember the spectrophotometer, all the things it spews out, one of them is the LAB values, and there's the B you can get from the spectrophotometer. And what the B value is, the optical properties are usually measured on these scales. So the B axis is usually a measure of yellowness or blueness. If it's a positive number, up the B scale, like this one is B1, then it's slightly yellow. If it's a B3, B equals 3, then it's quite yellow. If it's close to 0, it's neither yellow nor blue. And again, also from the A axis, if you have the A values, this is some information from a calcium carbonate from Greece. If, for example, this A value is nearly 0, so it's neither green or red. If it had a negative value, it would be greenish. If it had a positive A value, it would be reddish. So that's what you can get quite a lot of information from these A and B values. If they don't have it on the data sheet, you can probably ask for it. They're sure to have measured it. Okay, final secret is how scrub resistant will this filler be in the paint formulation. And it makes sense if you think about scrubbing something with a scrubbing brush. The harder it is, the less it will wear away when you scrub it. So hardness, obviously, is the parameter you want to look for scrub resistance. And most data sheets will report the Mo hardness value. So what is Mo hardness? It's a measure of the hardness of minerals. It was developed many years ago, and this table is an indication of hardness of minerals, where diamond is the hardest mineral, so it's got a Mo hardness of 10, and talc is the softest mineral, so it's got a hardness of 1. And the other minerals, these are typical minerals used in our industries, they're in between. Silica is pretty hard, as you can imagine. It's got a Mo hardness of 7. Kaolin is 2, and calcium carbonate 3, and all the others you can see. So if we go back to our kaolin data sheet, it's got the Mo hardness here, 2 to 2.5 as expected. And it's usually an intrinsic value of that mineral. So most kaolins will have a Mo hardness of 2. This silica, however, this is a silica we sell, has got a Mo hardness of 7 as expected. So the silica will have better scrub resistance than the kaolin or than calcium carbonate even. So these are the secrets we've discussed that you can get out of your data sheet. How pure is the product, and has it been diluted to make it cheaper? Look at the chemical composition. Is it calcined? Look at the LOI, loss of ignition. Are there upsizing opportunities? Look at the particle size and know the difference between mesh and microns. How white is it? Look at the whiteness measurement, bearing in mind that there are many ways to measure whiteness, and I've told you how to compare apples with apples. How yellow is it? Look at the B value. And finally, will it give good scrub resistance? Look at the Mo hardness. Okay, and then finally, I just wanted to show you that a lot of this information that I've told you, I know it's quite daunting when you don't deal with it every day like I do, is available on our website, kaolin.co.za, under the articles. And these are basically our newsletters written as articles. They take a technical subject and they try to I've tried to write it in a way that the man in the street can understand. Don't know if I always succeed, but that's what we're trying to do. And these are examples of some of the articles we have there for you to refer to anytime you want to. There's one on mesh versus microns that we've discussed, calcined kaolin, yellowness, specific gravity is not something we discussed today, but we've got a whole article about that. Hydrophobic versus hydrophilic, and there's lots more articles. So have a look in when you have time. How white is white? That's a difficult one to remember, all those different whiteness parameters. And then another resource we have on our website we call freebies, which are free downloads. And for example, you can get the mesh to micron conversion chart that I was talking to you about. You can also get the Mo hardness comparison chart that I showed you. We also have a chart of refractive indices, comparing them for the minerals that we've discussed, and a specific gravity comparison chart, which is also something that's usually on your data sheet that I haven't discussed today. And then we also have for free, a titanium-free contractor's paint formulation that you can download if you want to get ideas of saving money and not using any titanium. And then tips to reduce titanium in tint bases. So again, trying to build value and for our customers and give useful information on our on our website instead of just trying to sell you something.